Good morning, ma'am. Myself Praveena. I am from Triple B section. My topic is about transfer function to state space problem in control systems. Introduction to transfer function. Transfer function are mathematically representations of linear time invariant LTI system. They relate the system input to its output in the frequency domain. Understanding transfer function is crucial for control systems analysis and design. Transfer function is the ratio of Laplace transform of the output to the Laplace transform of the input. Consider all initial conditions as 0. What is state space representation? State space representation describes a system using state variables and equations. It provides a framework that captures the dynamics of the system in time domain. This approach is particularly useful for multivariable systems and nonlinear systems. State space. Importance of conversion. Converting transfer function to state space is essential for simulation and control design. State space allows for easier implementation of control algorithms. It also facilitates the analysis of system stability and controllability. Basic element of state space. A state space model consists of matrix A, B, C and D. The matrix A represents the system dynamics while B relates input to the state. C connects state variables to output and D represents direct transmission. I by O model to state space. Infinite many solutions are equivalent. Control canonical form. Transfer function definition. A transfer function is usually expressed as a ratio of polynomials in the Laplace domain. The general form is h of s equal to n of s by d of s, where n of s is the numerator and d of s is the denominator. The poles and zeros of the transfer function provide insight into the system behavior. Transfer function. Convenient representation of a linear dynamical model. A transfer function TF relates one input and one output. Converting from state to space to transfer function. X equal to Ax plus Bu. State equation. Output equation is Y equal to Cx plus Du. The conversion process. The conversion from transfer function to state space involves determining the A, B, C and D matrix. One common method is the controllable canonical form approach. The chosen method depends on the system's complexity and specific requirements. Controllable canonical form. In controllable canonical form, the state matrix A is structured from the coefficients of the denominator. The input matrix B is typically a column matrix of appropriate dimensions. The output matrix C is derived from the coefficients of the numerator polynomial. Example, y of s by u of s equal to s square plus 7s plus 2 by s cube plus 9s square plus 26s plus 24. Observability and controllability. Observability ensures that the internal state of the system can be inferred from the outputs. Controllability assesses whether the system state can be driven to any desired state. Both properties are crucial for effective control systems design and analysis. Applications of state space model. State space models are widely used in robotic control, aerospace and automotive systems. They facilitate modern control technique like state feedback and observers. These applications demonstrate the versatility of state space representations in engineering. Summary and conclusion. Converting transfer functions to state space model is a fundamental skill in control engineering. Understanding the process enhances the ability to analyze and design complex designs. Mastery of this conversion empowers engineering to effectively tackle real world challenges. Thank you for giving this opportunity.